Dear students, so let's learn more about the chapter current electricity. And the topic that we are going to learn today is a current through a simple circuit. Now, what do you mean by a simple circuit? A circuit is one in which we have a device called a resistor. Now, that is the symbol for the device resistor. Now, what is a resistor? Device which offers opposition to the flow of current is called as the resistor, and we measure the opposition in terms of a physical quantity called resistance, and the SI unit of which is ohm. Capacitor is the device. The ability of the capacitor to store charges is called capacitance. Similarly, resistor is a device which offers resistance. Now, that resistor can be in the form of a simple wire. Any conductor offers resistance. So, human body is a conductor. So, our body offers resistance to the flow of charges, but it has certain fixed opposition. So, that is why if the current exceeds certain limit, our body cannot resist that current, and that is the reason why we experience as a shock, as well as we may even die depending on the strength of the current. So, this is the notation used for the resistance, and I am going to write it as capital R is the symbol used for that. Now, we are going to connect a source of EMF. So, any device which provides electric energy is called as a source of EMF, and we denote that by capital E. So, E is the EMF of the battery, EMF of the cell. Now, that source can be in the form of an acid cell, which are normally used in inverter, or it can be even used in a number of vehicles. So, we use a battery, correct, that is called the acid cell. Then we have the dry cell, which we normally use in the torch, or so here we have a remote in which we use small cells. So, these are all the dry cells. That is electric generator. There are solar cells. So, these are all provides electric energy, and they are called a source of EMF. And when we construct this cell, we use one or the other conductor inside. It can be in the form of a plate, or it can be a coil, and that offers resistance, and that resistance offered by the cell itself is called as the internal resistance, which we denote by small letter R. So, what is the E? E is the EMF. What is capital R? External resistance. What is small r? Internal resistance, which is the resistance offered by the cell. And due to this cell, now it is a closed circuit. So, current flows, the direction of the conventional current is always from the positive to the negative of the cell. So, in reality, it is the electron that always moves from the negative to the positive, and conventionally the direction of the flow of the current is taken as always from positive to negative. So, altogether there are 4 variables are there: EMF, internal resistance, which is small r, external resistance capital R, and I. So, the relation between all these variables, and that is what we are going to write. Now, EMF is always measured in terms of volt, resistance is measured in terms of ohm, and the current is always measured in terms of ampere. So, the relation between these are 4 variables. Now, whenever the current flows through this circuit, the potential difference across the resistance, which is also called as the terminal potential difference, which is given by the Ohm's law, V is equal to I into R. And throughout the circuit, the current is the same, whether it is through external resistance or even through the internal resistance. Now, what is the potential difference across R, that is internal resistance? I will write that as V dash, which is equal to I into small r. And EMF is always the sum of these two potential difference, V plus V dash. So, V is equal to I into capital R, V dash is I into small r, I is common, we will get R plus R, and there we get an expression for current. I is equal to E by R plus R. So, this is the expression for current through a simple circuit. So, current through a simple circuit is given by the ratio of EMF divided by sum of the resistance of the circuit, that includes the external resistance and internal resistance. Sometimes we connect more cells in the circuit, we connect more external resistance. In that case, we write the current equal to I is equal to E equivalent, that is the net EMF, R equivalent plus R equivalent. So, we use this equation when there is only one cell, one external resistance. If there are many, then we use this particular formula. Now, V is given by I into R. We can even write here E is equal to V plus this I dash, sorry, V dash is nothing but I into small r, I into small r. So, from this, so what is the V is equal to, if you rearrange, I will get V is equal to E minus IR, E minus IR, which you can write here. So, V is equal to E minus IR. This is one more format of the equation to find the terminal potential difference. There is one more, that is, we know I from here, right, which is E by R plus R. So, this is I and then multiply by R. So, it is E R by R plus R. Therefore, to find the terminal potential difference, there are different formats of the equation. One, terminal potential difference is given by the Ohm's law, which is V is equal to IR, or E minus IR, which is in terms of EMF, current and internal resistance, and again one more, which is ER by R plus R. So, all these equations are important while solving the problem. So, hope you have understood the current through a simple circuit. So, current through a simple circuit is given by the formula I is equal to E by R plus R. If there are many cells, we use I is equal to E equivalent by R equivalent plus R equivalent. And this expression for the terminal potential difference. Remember, in a simple circuit, the current is same throughout the circuit, So, now let us see, when cells are connected in series, what is the current through such circuit? Series combination, in a torch light, we place one cell behind the other, connecting end to end combination. Now, this is called, and when switched on, we get the light. Okay. So, what do you mean by connecting cells in series? We can connect any number of cells in series, but to analyze, I am going to connect only two cells. So, this is one cell, this is the other. The first cell has EMF E1. The first cell has EMF E1 and internal resistance R1. The second cell has EMF E2, internal resistance R2. We can connect again many more cells. Now, to this, I am going to connect only one external resistance. We can connect any number, but this is for easier understanding. So, this is a simple circuit, cells in series, and current is same throughout the circuit, current I. Now, if I can replace this equivalent as one single cell, E equivalent, comma, R equivalent, then there is only one resistor. So this is a simplified version of it. These two cells are replaced by one single cell whose equivalent EMF is given by E equivalent and R equivalent, and R is the external resistance. Let V be the potential difference across the combination, and let V1 be the potential difference across the first cell, and let V2 be the potential difference across the second cell. So first let's write what is the potential difference, and I is the current. Here also the current is the same, I. And in series combination, as I have told you, current remains the same. So first let's write potential difference across the first cell. Potential difference, various formats are given. V is equal to IR, V is equal to E minus I into R, and V is equal to ER by R plus R. These are the three different formats which are given, and I will use the second one. So first, potential difference across the first cell, V1 is equal to E1 minus IR1. Across the second, V2 is equal to E2 minus IR2. As you can see, the current is same. Okay. So now what is the potential difference across the combination? V, which is given by sum of the potential difference across each cell. So what is the V1? V1 is here, E1 minus IR1 plus E2 minus IR2. Now combine the EMFs E1 plus E2 minus I into R1 plus R2. Correct? Minus I1 minus I2, minus I is common, you will get R1 plus R2. So this is the effective potential difference. Now what is the potential difference across the equivalent, which is V is equal to E equivalent minus I into R equivalent. So this potential difference and this across the entire circuit has to be the same, because this is the equivalent circuit, right? So now when I compare here, I will get E equivalent is equal to E1 plus E2. R equivalent is equal to R1 plus R2. So to generalize this, if there are many, then we can write like this: E equivalent is equal to E1 plus E2 plus E3 and so on up till En, nth cell. R equivalent is equal to R1 plus R2 and so on plus Rn. And how do we find the current? I is equal to E equivalent by R plus R equivalent. This is how we can find the current. How to find the potential difference across the combination, which is here. V is equal to E equivalent minus I into R equivalent. So these are the different formulas for the effective EMF, effective internal resistance, current through the circuit, and the terminal potential difference. So this is so therefore the advantage of combining cells in series is that the EMF will get added up. So we'll get more EMF in the circuit, so that a larger EMF can be used for any practical purpose. Now what if the cells are identical? For identical cells, okay, for n identical cells. If the cells are identical, then the EMF is same, E plus E and so on, n terms. That's why E equivalent is equal to n into E. What happens to the internal resistance, R equivalent? R equivalent, again the same thing, it's R plus R plus R. So n such terms, it becomes NR. Okay. And now the formula for the current, I is equal to E equivalent is nothing but NE, N into E, divided by R plus R equivalent is equal to N into R, NR. Okay. So, when this is only for identical cells, only when the cells are identical we can use this. Okay. What do you mean by identical cells? Cells having same EMF and same internal resistance. So, E equivalent is equal to E1 plus E2 plus E3. So, it becomes NE and internal resistance becomes NR, so that we can find the current through it. So, potential difference, as usual we can use this particular formula. So, V is equal to E equivalent minus I into R equivalent. So, important derivation, important question, that is cells, when cells are in series, derive the expression for current through the circuit or derive the expression for equivalent EMF and equivalent internal resistance can be measured using all these formulas. So, advantage of the cells in series is that the effective EMF increases or becomes larger. Next we have cells in parallel. So, again this question derivation is important. Let us see now what do you mean by connecting cells in parallel. Whenever the cells are in parallel, we connect the positive terminal of the cell together and the negative terminal of the cells together like this. And then from these points an external resistance is connected, capital R. So, first cell E1 and R1, E2 and R2. Now, the first cell sends a current I1, the second cell sends a current I2, and these two currents will get added up to become the main current. So, these are branch currents. So, that I is equal to I1 plus I2, and in parallel combination potential difference is same. In series combination current throughout the circuit is same, whereas in parallel combination potential difference is same and the current I is equal to sum of the two currents. Now, when I find equivalent, we can replace these two cells by one single cell whose EMF is E equivalent and R equivalent, and then external resistance capital R, and then the current I, and V is the terminal potential difference. So, in series combination current is same, in parallel combination potential difference is same. So, let us write the expression for potential difference across the first cell. I am using the same format. So, V is equal to E1 minus I1 R1. So, I will rearrange here, it is a V plus I1 R1 is equal to E1 minus V, or I1 is equal to E1 minus V by R1, that is the current through the first. Similarly, current through the second I2 is equal to E2 minus V by R2. Now refer the equivalent circuit. So where we have V is equal to E equivalent minus I into R equivalent. Okay. So these are branch currents. So when we add these to branch current, we get the main current I. So I is equal to I1 plus I2. So what is I1? I1 is E1 minus V by R1 plus E2 minus V by R2. Here now when I divide both the terms by R1, the first term that I am going to get is E1 by R1. Then here plus E2 by R2 plus E2 by R2. Here the second term minus V is common, minus V into 1 by R1 plus here also we have that term, minus V by R2. Minus V I have already taken out, so I will get 1 by R2. Now based on this, I can write an expression for I similar to this. I is equal to E equivalent by E equivalent minus V by R equivalent. Or we can write like this, E equivalent by R equivalent minus V by R equivalent. Okay. So therefore the expression here which we are going to write I is equal to E equivalent by R equivalent minus V by R equivalent. Now you compare on both the sides. We find that this ratio is equal to this. So E equivalent by R equivalent is equal to, if I compare this with this, we get E1 by R1 plus E2 by R2. If there are many cells, then we can write like this, E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2 plus E3 by R3 and so on plus En by Rn. Then compare this, minus V by R equivalent is equal to minus V into this. That is why 1 by R equivalent is equal to 1 by R1 plus 1 by R2. If there are many, you can write 1 by R equivalent is equal to 1 by R1 plus 1 by R2 and so on plus 1 by Rn. Okay. Now what if the cells are identical for n identical cells? So before that, let me simplify this further. So from here, 1 by R equivalent is equal to 1 by R1 plus 1 by R2. We can write 1 by R equivalent is equal to, take LCM here, you will get R1, R2 and then R2 plus R1. So that is why R equivalent is equal to R1, R2 by R1 plus R2. So that I can substitute here and then I can bring it this side. So we have E equivalent is equal to, if I bring R equivalent this side, so then I will get this term R1, R2 by R1 plus R2 into, take LCM here, you will get R1, R2 again, R1, R2, then E1, R2 plus E2, R1. So this term will get cancelled. So you will get a formula, E equivalent is equal to E1, R2 plus E to R1 by R1 plus R2. So, we can use this only for two cells. So, R equivalent is equal to R1 into R2 by R1 plus R2 for two cells, or E equivalent is equal to E1 R2 plus E2 R1 by R1 plus R2. An expression for current, that is I is equal to E equivalent by R plus R equivalent. That is the formula for current through the circuit. Okay, now coming back to this, for n identical cell, for n identical cells, all right, here we have 1 by R equivalent, 1 by R equivalent is equal to 1 by R plus 1 by R plus and so on, 1 by R, nth term, so it's n by R. Therefore, R equivalent is equal to R by n. How about the cells here? E equivalent by R equivalent is equal to, we have E by R plus E by R plus E by R, and so n terms again. So, n into E by R, or E equivalent is equal to R equivalent, which is R by n, R by n. This is R by n, which I have to write here, then into n by R, and then E. So, this R and will get cancelled, therefore, we will get E equivalent is equal to E. Okay. So, which means when n identical cells are connected, the equivalent EMF is same as one single cell. So, that is why the expression for current goes like this now, I is equal to E equivalent by R plus R equivalent, which is I is equal to, what is E equivalent, which is the E, capital E, by R plus, what is the R equivalent, R by n, R by n. So, on simplifying you will get I is equal to n into capital R plus small r, and then this n goes to the numerator and it becomes NE. So, I is equal to NR by R. So, that is the equation which we use when n identical cells are in parallel. So, plenty of equations are there. These are all important. The derivation is important, and formulas are important even to solve the numericals as well. So, in the next class, I will explain more on this chapter, as well as we will solve some more numericals which is remaining. Okay. So, reminder regarding the test which I am going to conduct this Sunday, and Saturday we will have an interactive session. And again a reminder for those who have not paid the fees, pay. So, before we take some more action against you all. Okay. Thank you.